Tom. Tom Beucler is a professor of environmental data science at University of Lausanne in Switzerland. He leads the data-driven atmospheric and water dynamics laboratory. He did his PhD in MIT, where he studied atmospheric science and mostly tropical convection. And then he did some postdoctoral work at Columbia University, UC Irvine, with a focus on deep learning for climate modeling. So his website tells me that he likes plenty of things, including jogging, hiking, and cats. And so I will finish the introduction with a quote by Norbert Wiener saying, "The best material model of a cat is another, or preferably the same cat."
Well, thank you, David, for the introduction, and thanks to the entire organizing committee for inviting me today. I'm really happy to be here. So today I'll talk about artificial intelligence pathways from weather to climate, and this is based on an upcoming survey with many colleagues, and I'll mostly be presenting published work with some of my group members, and I can't list all the names here. We are very, very collaborative field, machine learning for weather and climate science. So this is not a one-person work. It's really the results of years and years of collaboration. As a quick introduction, I think David already said it. I lead a group in atmospheric, exploring the intersection of atmospheric physics and AI, how the knowledge we have of our climate system can help guide machine learning algorithms, but also how these same algorithms, coupled with the troves of data we have about the Earth system, can help us better understand it. So I work generally in environmental data science with a particular focus on improving Earth system models, which you can think of as a more general version of climate models. But what I'm going to be starting with is our work on weather models. So we have a particular focus on extreme weather events, how to better forecast them, how to zoom in. And I guess we're in small committees, so don't hesitate to interrupt me if you have any questions at any point. So I want to start with the forecast for Cambridge. So I just went on the UK Met Office website, and we're getting a brief respite, and then we should get some rain again on Wednesday and Thursday. But what's incredible is that now, on your laptop, you could also be running AI weather models. So here I'm giving two examples of AI weather models. Again, for this week, you can look at Cambridge if you want. You're going to definitely get, well, it's very likely that we will get rain. At the top, actually, for this particular forecast, it's quite predictable. You can see that the model at the top, GraphCast from Google DeepMind, and the model at the bottom, called AIFS from the European Center for Medium Range Weather Forecasting, a lot of it is based in Reading, are very close. If you're curious, I can explain a little bit more about the situation, but what I mostly want to communicate is that in just a couple of years, we've really witnessed a revolution where we can have state-of-the-art AI weather models that you can just run on your laptop. That was non-existent 3 years ago. And part of that is that weather forecasting can be framed quite cleanly mathematically, which makes it a very good problem for machine learning. It can be framed as a mostly initial conditions autoregressive problem. So, assuming you know the state now, you don't always know it, but you can assume you mostly know it. So these are three-dimensional fields of temperature, how much water there is in the atmosphere, winds, etc. The goal is to predict the weather at now plus what we call a lead time. And GraphCast, the model I just showed you, a couple of years ago started rivaling the model in the middle, HRS. So this is the forecast of the wind. You're looking at wind magnitude, how fast the wind is blowing. And the model in the middle used to be our best traditional weather model that runs on thousands of CPUs. It used to run in Reading, now it also runs in Italy and Bonn. And at the bottom, what you have is GraphCast. That can run on just one GPU. Of course, it takes more to train, but once it's trained, it can just run on one GPU. And according to one standard metric, so this is based on for example, mean squared error, root mean squared error, metrics that really encourage you to predict the conditional mean state. These models have started beating our traditional model with a big potential for democratization. And I don't know if I was maybe gonna write equations. I don't know if it's a good idea. If we can't see them, you just tell me. The reason it's so easy, since we're in a mathematical institute, I thought I'd try it out. It's actually, mathematically, it's extremely simple. For the deterministic model, you're just predicting the next time step based on the previous time step. And what the machine learning model is learning is just this forcing term, which is a function of the previous time steps. But generally, you're just looking at one step back. It's usually a Markov process of order 1 or just order 2, and you can get away with it. And so it's as simple as just learning this function f with a neural network, and the most successful architectures are based on graph neural network and 3D transformers. And what's crazy is numerical integration-wise, you can see how simple this is. This is much simpler than traditional model. You can just, this is just a Euler integration scheme, and the machine learning implicitly learns it. And so if you look at the progress as a function of years, the 100 mark is when AI models started beating traditional model. According to specific deterministic error metric, more deterministic oriented error metrics, here we're looking at root mean squared error of the mid-tropospheric geopotential height, which tells you where the ridges and troughs are. So, you know, for example, if you, like we're getting winter storms right now, it's telling you where they are and how they're propagating. With an explosion of models as soon as, so, you know, GraphCast is here, the model I just showed you, AIFS is here, an explosion of models post 2023. But as scientists, we're interested in more than just weather. So we're interested in more than the weather that you're going to get in 6 hours to 2 weeks. We're interested in how our entire Earth system is going to change, what we refer to as climate. But the point I want to make here, and that's really the point we want to make with that survey, is that AI for weather and AI for climate are separated by more than lead time. And this is why it's going to take so much longer for artificial intelligence to revolutionize the way we project the climate. People will tell you weather is an initial condition problem and climate is a boundary conditions problem. It's a bit misleading because both of them are initial and boundary conditions problem. But what you can say is that the weather, based on today, you're going to predict the state in a couple of days. Because of the chaotic nature of the atmosphere, this only works until a certain time. So the weather has a nice property of being paired, so you can frame it as supervised learning. Meanwhile, the climate problem, it's not just that you're looking really far ahead, and so you lose predictability, and you're predicting conditional statistics. So you're saying, okay, what's on average going to be the temperature of England in this new climate? It's more that you want to explore and imagine worlds you may never observe. So we're not just predicting the future climate, we're predicting many different future climates in response to many decisions that we could make. We're only going to make one set of decisions, we're only going to observe one trajectory, but if your model is good, it should be able to model what we call a counterfactual response if you do a bit of causal machine learning. And so it's a lot harder, because now you have this generalization problem. But you could argue that actually the generalization problem is a bit of a unifying thread, and that's what I'm going to use. So I'm going to introduce the concept of out-of-distribution, and here I'm introducing it in a pretty simple way. So I'm one of the applications talk, right? I'm sure some of the mathy talks will do a much nicer job than I will. Here I'm just looking at the marginal distribution of how humid the atmosphere is. One of the challenges, for example, in the future climate, our atmosphere is going to be a lot more humid. The tails, the most extreme humidity, is going to be much higher if you think of the mass of water vapor that the atmosphere is going to hold. Out of distribution doesn't have to be on just one variable and just the marginal distribution. It could be in the joint distribution of inputs and outputs. But for now, that's one of the biggest challenges we have in our field. I would argue that's one of the biggest challenges that applied machine learning has in general. It does very well at interpolation. It's much, much harder to do extrapolation, especially in OOD scenarios. And that's visible in both the AI for weather case. So that's a recent paper by Sun et al. You'll see the dates. A lot of the research is very recent. We're a really active field, and we talk to each other a lot. So you'll see a lot of 2023, 2025, 2026. That's a recent paper where they took one of the top AI for weather models, and they got rid of all the most intense tropical cyclones, and then they retrained it, and then they found that they could not predict the most intense tropical cyclones. That's a clean example showing that even these AI for weather models that look like they're doing really well are really struggling to predict events that they've never seen in their training set. I work a lot on AI for climate, so I train models inside climate models that are going to represent processes we don't understand. I'll get more into it. Here I'm predicting the responses of storms in a climate 8 Kelvin warmer, so whose surface is 8 degrees Celsius warmer than the training set. And if you do that with a neural network, you can get errors of order 10. So you're predicting 10 times the value you're supposed to predict. You don't need to do that poorly. It depends on your activation function. But we get such a big and clean error that it's a really nice demonstration that you shouldn't trust AI for weather or AI for climate in the out-of-distribution cases. And so this is going to be the unifying thread of my talk. I'm going to show some results where we've tried to tackle this challenge in both the weather case in applied to tropical cyclone forecasting, tropical cyclones remaining some of the most devastating and deadly weather phenomena. And so these are preprints, so they haven't gone, I mean, the first one is like pretty much through peer review. The second one, we've been working on it for years. It's been improving, but I'll note archive whenever it's a preprint to distinguish the fully published results from the peer review. But these are pretty mature results. And then for the climate case, I'm going to compile a bunch of recently published papers and preprint and tell you a little bit about how to address this OOD problem by combining physics and machine learning to form what we call hybrid AI physics climate model. And then because it's part of the review, I'll talk a little bit about how to quantitatively make a first step towards evaluating what does AI really buy us in terms of scaling. Because we hear a lot that AI is making everything faster, but I find that we don't spend enough time actually crunching the numbers and making sure that's happening. Okay, so I'm going to start with tropical cyclones. So that was a focus of my research group. And I'll motivate it with a case study. This case study is Hurricane Otis. It's a hurricane that hit Mexico, Acapulco, in October 2023. And it was extremely challenging to forecast. So it looked like it was just going to be tropical storms, no big deal. And then it intensified. So to give you, so this is a video. It's hard to take videos in the middle of storms. So usually when you go and try to look for videos, you mostly find like cameras, shakings, etc. It produced a lot of damage. And the reason it produced so much damage is it underwent what we called rapid intensification. So that's just a conventional classification. It's a tale of how quickly surface winds can intensify. It corresponds more or less to intensification that are more than 15 meters per second in 24 hours. And so this is what it looked like. So this is infrared imagery from the GOES satellite. On the left is what it looked like on October 24th. The max wind were 45 knots. You can divide this by roughly 2 to get the meter per second. So this is the maximum surface wind, which correlate quite well with the wind damage and can inform also the storm surge. Most of the damage, if you don't know from tropical cyclones, comes from the storm surge or flood damage. It can be quite deadly and devastating. And then the official forecast said, okay, in one day it will get to 55 knots. And so it will be a tropical storm, be careful, but you know, it's gonna be okay. And then in reality, it reached 155 knots in one day. And so it was a hurricane of category 5, and Acapulco was not prepared, and it was devastating. And here I'm using the Weather Lab tool of Google. I don't work for Google, but I love this tool. And it allows us to quickly visualize how different models made their forecast. The truth is in black, so here you can think of it for now as a time series prediction where you're predicting the intensity. So the max surface wind speed at the top, the minimum sea level pressure at the bottom of a tropical cyclone. The truth, the ground truth observations of S-tracks are in black. And in yellow is the best traditional model. In purple is GraphCast that I showed you earlier. What you can see is like they completely missed it, right? None of them were able to get this rapid intensification. And so the press jumped on it. They were like, okay, AI weather forecasting looks good, but it's not ready yet. Be careful, don't trust it. And they were right, it wasn't ready to handle such extreme events. It stayed relatively flat when it should have predicted at least a high probability of an intense tropical cyclone happening. But what's funny is it coincided with the development of the next generation of AI weather models, so we already through like 3 generations now, which is the probabilistic version. And I'm wondering if I should keep writing a question or if I'll run out of time. I'll just do it for the weather case. So in that case, what you do is you acknowledge that you don't want just the most likely answer. So if you just do a deterministic forecast with a mean squared error function, what you're estimating is the mean state condition on initial condition. So you're just estimating a very blurry field of the future. Instead, what you can say is I have a distribution of possible states given my initial conditions, and then you can explicitly, I guess I don't need to write it, it's pretty clear here. You can explicitly model it here. Now I'm going to target this p theta. I'm going to learn a distribution condition on the previous time step. Same thing, most state-of-the-art model do a Markov chain of order 1, max 2, so you don't really do more than 2 time steps. And here you can use several techniques. People jumped on diffusion, of course, but if you cleverly perturb your initial conditions, or if you inject noise in the middle of the model, you can get similarly well-calibrated models, and it's well-calibrated with respect to what we call proper scores. So there are these proper scores that give you guarantees on how well-calibrated this P is, and allow you to get these full distributions, at least to calibrate them in the, for the marginal, we use what's called continuous rank probability score. If you're really excited about it, you can do the energy score for the multivariate version. What's important though is that now it has a shot at capturing extremes, because it's not just doing the smooth mean, it's getting the full distribution. Now the problem is that, so Google came with GenCast, which was a diffusion upgrade of GraphCast, but they only evaluated the tracks on the track they were able to predict. And so that motivated us to first develop our first versions. We wanted to specifically target tropical cyclones, but also objectively evaluate them. So if we have this set of observed tropical cyclones, how well do these different models do? And the reason these models don't do so well is that they train on what we call reanalysis, and it's the best estimate of the state of the atmosphere, but at 0.25 degree resolution. So you can imagine a very, it's 25 kilometers, still high resolution, but it has no chance of getting the really intense wind gusts we get from tropical cyclone. And so our thought is, okay, what about if we directly take observations and then we learn a distribution of the observations of interest conditioned on the previous states? And we wanted to do it the simplest possible way. So, our motivation, to give a bit more context, was as follows. We said, okay, we have these neural weather models, they're super powerful, but what they do is they predict a coarse environment that may be informative, but it doesn't really have the extreme events we're interested in. But we can look if that environment has information. So we did that in previous studies, and we found that we scored different models with respect to how useful they were for severe weather warnings, in particular related to convection, so thunderstorms. And what we found is that at least 2 out of 3 models, so in that case, it's Penghu, a model by Huawei, and GraphCast, the model I showed you earlier, were doing well enough at giving you an environment from which you could infer thunderstorms. They wouldn't directly predict the thunderstorms, but they would give you the environment in which the thunderstorms lived. And for tropical cyclone, you can see a little bit the same thing. This is the forecast. You're not exactly getting the tropical cyclone, but you're getting enough information that you could infer the distribution of possible tropical cyclones. And so then the first idea is to just take that environment and post-process it. So we framed the problem as a regression of time series with known initial condition. So we really wanted to do it at the global scale. There's a lot of studies focused on North America, with the Atlantic and the North Atlantic and the East Pacific, because I mean that's where the money is. But being in Switzerland, we thought, okay, we want to do something global, and if you want to do something global, you have to work with less good data. So the best you can have at the global scale are time series of where the tropical cyclone is, that's the track, and time series of how fast the winds are, the maximum, the block maximum, if you care about extreme value statistics, and that's what we call the tropical cyclone intensity. And now, all we have is we have to predict a time series of 2 variables. You can target a couple more, but that's a good start. And what we do is we position ourselves in the same shoes as a forecaster. So we say, okay, we know what the initial storm is, where it is, and how intense it is, which is roughly true. You know it within like 6 to 12 hours. And then based on that, we want to predict how it's going to evolve, and for example, whether it's going to rapidly intensify or not, to give you the example from Hurricane Otis. And so a strategy, which is really simple, we said, okay, what is the simplest possible model to do that? And this is work led by a grad student in my group, Milton Gomez, is we took the initial conditions, and then we use these neural weather forecasts that came out, so it could be from ECMWF, Google, etc., to forecast the environment. So now you go from the initial condition to the environment. I showed you, you evolve the environment. And then our simplest possible idea is we're just going to do distributional regression on the predicted environment. And so then you could, in the simplest case, just say, okay, I'm going to do a conditional normal distribution. Well, not even. In the deterministic case, you can just optimize it with mean squared error, for example. And in the probabilistic case, if you do a conditional normal distribution, what you can do is you can use proper scoring. So, I don't know, how many of you, just a quick, how many of you, can you raise your hand if you've ever heard of CRPS before? Okay, so half of the room. Okay, so I won't be too long. What it does is it measures the difference in the squared cumulative distribution function. And based on that, you can calibrate your conditional distribution. And what's nice is if you make an assumption, for example, you have a conditional normal, then you can write it explicitly, then it makes it super easy. If you don't, you can do it empirically by optimizing fair variance of the CRPS. And then we can say, okay, now we trained a full model, I'm skipping over years of work, and you can go back to Hurricane Otis at the beginning and you can ask, how well do we do now? And here's a new model by Google that's not published yet. It's called FNV3. That's the blue curve. It does really well. It's not published yet, so we don't really know what it does. It probably is also trained on observations, and it's relying on, that they said publicly, it's relying on FGN, which is a new version after GenCast. But then, if we do our simple post-processing, we actually do pretty well, even on tropical cyclones in the test case. It's just one vision of it, right? Unlike Google, we don't run it operationally. It's an academic lab project. But what's nice is even with a simple conditional normal distribution, but it's conditioned on an entire neural weather model forecast, right? It's not a naive conditioning. We ran an entire neural weather forecast, and by conditioning a simple distributional regression on that, we can predict the intensity of extreme events. So this is nice, and the other project that I'm not going to spend too much time talking about is we made a whole benchmark data set out of it to see how well model did in this setup where we following an initial disturbance, and what we found is that this strategy works really well. And Google's upcoming model, which I'm sure is going to be like, the preprint will come out in the next 6 months or something, also does really, really well. But all the other models are way underestimating the extreme events, which is normal because they're trained on this global environmental data, so you don't expect them to do too well. But there were a lot of claims. They do well on tracks, but they don't do well on intensity. But the good news is, even if they don't do well, they give you enough information that with just a tiny layer, you can recover the extreme events. So that's really encouraging because it means that forecasting extreme events is possible, especially if you retrain using the appropriate observational products. And given how many groups are getting results on that topic right now, I would say like the next generation of AI weather models are going to be able to get pretty good forecast of extreme events, which is kind of insane. I mean, 4 years ago, we couldn't run global AI weather model on a GPU, and now we're already discussing of extreme events, which are notoriously hard to forecast. So the progress in AI for weather is incredibly fast, and that's very nice. Before I switch to climate, are there questions? Yeah.
So is there a general definition of, an extreme event?
Yes.
I mean, what are they? Circular storms, floods, things of that sort?
In the broadest sense, I couldn't give you a single definition because it's true that we use it for many different types of extreme events. In this particular case of tropical cyclone, what we look at when we look at tropical cyclone intensity is the maximum sustained wind field measured at the surface. In practice, it's more reconstructed than measured from satellite observation. Boy, sometimes they fly drones or they fly a very brave plane in there. And it corresponds to a block maximum in statistics. So it's just the maximum sustained wind speed in a given period. So it's a block maximum, more than a threshold exceedance. But in some other case, for example, for flooding, when we care about return periods, we're more looking at threshold exceedances. But in that particular case, it was predicting a block maximum. Does that answer your question? Other questions? Yeah?
So could you use the same some way of forecasting to predict flooding, to predict a variety of other extreme events?
Yeah, no, and that's a really promising thing is now that we have these models that are really cheap and fast to run it's also thanks to this incredible reanalysis that are being put out by, for example, the European Center for Medium Range Forecasting, that we're getting models that are able to forecast the entire world at a pretty high resolution. And then all you need is an observational data set. And if you think that forecast gives you enough information, all you have to do is to post-process it. People will argue that you can also fine-tune or jointly train, so that's the philosophy behind foundational models or tell neural networks after foundation models, that you need a lot more compute to do, and you have to balance the loss function of many, many different terms. So it can be a bit trickier, but that can also be done. But I think to order one, there's a lot of potential to just take some of these top models, get a nice series of observations, and just post-process your AI weather model to, the variable you're interested in. Of course, you should be very careful with cross-validation, but the best test is always to run it live. Like if it's a phenomenon you observe often enough, and that's what Google did actually with the FNV3, you just freeze whatever model you trained, and then you test it on real live cases, and that's the ultimate test, right? There's nothing harder than this. There's another challenge that I didn't talk too much about is how to get your initial conditions. And that's a whole field, data assimilation. The advantage is the initial conditions for these neural weather models are quite easy to get. Now, the initial conditions for the phenomenon you're interested in, it's going to really depend on what you're interested in. So each phenomenon will have their own team collecting data, right? So I don't know what kind of flood you're interested in, but it really depends on the agency that's responsible where you're interested in. Yeah?
Okay, just a quick.
Yeah.
When you show the probabilistic models,
Yeah.
when you sample basically the next step from a probabilistic model,
Yeah.
It seemed like from the equation you showed, it seemed like these models are kind of trained to be trained on a specific temporal resolution. Is it right, on a specific delta t.
Correct.
Every model has its own.
I mean, there are people doing neural differential equations and neural operators, but it's more, I would say it's more experimental than practically useful. So people do it more for fun than because they actually need it. But I like to do things for fun. But yeah, neural differential equation and neural operators are the continuous equivalent that people have been playing with. Yeah. Yeah.
How are we in practice enforcing the physics into the model? Is it through the observation, or are you actually doing like a pins approach in which you enforce the residual?
There's no physics in AI for weather. I mean, in the base AI for weather model, there's in appearance no physics. Now, big asterisk here because this whole data you trained on is from a physical model who has ingested observation, so you're implicitly learning the physics that were used to produce the data. But, and I'm a physics-guided ML expert, so I love physics-guided machine learning. Much more general than PIN. For me, PIN is just one tiny example of everything you can do, right? But in AI for weather, you don't really need to enforce anything, and that's because it's such a paired problem with a ton of data at short horizons. There are nice papers showing that if you enforce global mass conservation, global energy conservation, you can do a bit better. It's a paper from the NCAR team, DJ Gagné, etc. They did it on Fuji. They took Fuji, they added mass and energy conservation, and it does a bit better. But it's not a big difference. For weather. For climate, it's really important. And maybe good transition. I'm going to switch to climate. So in climate, we don't have a truth, right? We don't know, we can't observe the future, we don't know what's going to happen. What we want is a model we can really trust. We've observed what happened in the past. We've observed one realization of what can happen in the past. And I think something we want to do in that review and in general is clarifying, and especially for statisticians and machine learners, a little bit what we expect from the climate models, because a lot of really, really talented and clever people are coming and saying, okay, I'm going to use all my AI skills or statistical skills for climate. So I think it's nice to spell it out. This is adapted from Tapio Schneider. He showed it last week at the conference, so I borrowed it. But it came from discussions we all had together, so. Okay, to first order, what we want is we want to understand, yeah?
Question, like, how do you train those kind of models? Do you use some kind of teacher force or some kind of case type rollout?
For weather or for climate?
Like this one, this very basic one.
The weather one, right? Yeah, I could point you to reviews. In the simplest case, it's a progressively longer rollout. So you start by predicting 6 hour ahead. Once you're done, you do 12 hour ahead. Once you're done, you do 24 hour ahead. And then there's reviews now that tell you like what works and what doesn't work, but many of these models are trained like that, just with progressively longer horizons.
Okay, and how do you, because like at least for dynamical systems in physics, sometimes when you try a very big rollout, you have some kind of chaotic.
Correct. So in the weather, you don't really touch that. It's really at what we call the subseasonal to seasonal time scale. That's like starting at 3 or 4 weeks ahead that you start to really hit the limit of predictability.
Okay.
And that's when you switch to climate. Eventually, you're just interested in conditional statistics rather than the exact state.
Okay.
But when you're in the weather, you're still in a problem that's heavily influenced by your initial conditions. So you're always in a paired case, and you just have to go further and further and further in time, and it's stable up to that time. You have no guarantee of stability after that.
Thank you.
Okay, so what do we expect from climate models? Well, we want them to help with our understanding of the Earth system and ideally also policy. So what we want to know, for example, is if different countries emit different kind of greenhouse gases, mostly CO2, we mostly think of equivalent of carbon dioxide, but methane is also a greenhouse gas that's of high interest. How will climate change? And that includes, for example, clouds that are like small scale and have non-trivial responses. Aerosol forcing. How will aerosol emissions, so that you can think of that as pollution, change the climate, including through the indirect effect. So they do reflect sunlight, but they also change how clouds are formed. And what we want to understand is even if a country that has never emitted aerosols before starts emitting aerosols tomorrow and another one stops, how will that affect the climate? And that's a big deal because if we removed all of the pollution today, we could actually gain an extra degree of global warming. So you do care about how polluted the air is if you want to understand how the Earth system will evolve. And finally, the carbon cycle, more generally biogeochemical cycles. How much of that emitted carbon dioxide will stay in the air versus how much will go in the ocean, will be stored in forests, etc. And what you want, ideally, is not just the equilibrium state, you want the full transient, spatio-temporally resolved state as a response to conditions you may have never observed and that you may never observe at all, right? You want to maybe dream that that country will completely stop emitting carbon dioxide, and you want to say, okay, if that happened, this is how the Earth would evolve. This is a really hard challenge. And in that review, because this slide is more experimental / opinion, we brainstorm a bit about, okay, what are the minimal things you would want to do for your Earth system model to be able to produce those responses. So we said, okay, if we start from, and then it's easier to think continuously here. When you integrate for so long, it's easier to just think of it as coupled ODEs or coupled PDEs. So you take all your fields of interest, temperature, moisture, the 3D velocity field, biogeochemical tracer, your ocean state. You can write it as an ensemble couple ODE. And the advantage of machine learning, you'll hear a lot, is that it's cheap, so you want to produce large ensemble to sample all your different possibilities. And the idea, and that's something I'm not going to talk too much about today, but I work a lot on, is that there's a resolution that you need to integrate the whole response forward. But what machine learning can also do is that if you want to zoom in for a particular region or a particular village or something, you can just take that whole simulation, take a small part of it, and zoom in. That's super resolution algorithms, and machine learning is also very good at that. What we argue is that all you need to do is to, at minimize, to categorize your forcing a little bit. So if you're advection, you transport term, and what you want is you want to respond to scenarios. So if you read the International Panel of Climate Change, the scenarios mostly, I'm making it a bit simpler, prescribe 3 things. How many greenhouse gas we're going to emit. And that mostly goes in the radiation scheme. It's a greenhouse effect, it's like a blanket on the infrared, for the infrared wavelength, and it's going to trap heat. And so what's really important, if you're going to design a new model from data, is that that goes in the radiative scheme, and that only touches temperature or thermodynamic variables that are very close to temperature. Because if you just learn without taking into account the confounding, you could, learn a relationship, direct relationship to wind, which would make no physical sense. For aerosols, you want it to go to the temperature. For example, you've heard of geoengineering probably. Sulfate reflecting sunlight, that's a direct effect. But also, these little seeds, that pollution, it helps form clouds. So you also want a little bit to go in that forcing, what we call the subgrid scale forcing. And finally, you'll get scenarios about how people will change, the agricultural surface of the countries, etc. That's called land use and cover changes. It changes the albedo of the Earth, just like, if you lose snow, you reflect less sunlight. And the surface properties and fluxes also change the turbulence, etc. Okay, so that's more of an opinion of if you were to design a climate model from data, the most important thing is to at least restrict your forcing so that you have some basic causality in whatever you design, and that should help you have an answer to these scenarios. It may not be the right answer, but at least you'll be able to have an answer. Surprisingly, a lot of AI for climate efforts don't pass that bar. And so they can't even answer different scenario forcings. So you should anticipate the kind of questions you want to answer. That's the message. I'm not going to cover all the AI for climate efforts, but I did spend a lot of time last year and the 2 previous years compiling them in the living review on GitHub. There's dozens and dozens and dozens of paper if you want. I think I have the biggest living review for AI for climate. I try to group all of the team's efforts. And I think from that, we've identified mostly 2 promising solutions for the out-of-distribution AI for climate problem. The first one is based on emulation. This is not my work. This is work I'm a fan of. But where you take an existed, we stuck with that challenge of being able to produce responses for things we've never seen. So how do you do that? Well, one way is you start from a climate model that exists that already does it well. And then you run it for many, 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 many different situations. You collect all this data, and then you emulate that climate model. And this is an example that's doing it well. It's called the ACE2 climate model emulator. It was developed by the AI2 team in Washington State. And then recently they coupled it with the Samudra ocean emulator from the M2 Lines project, which is mostly, spans the US, but it's mostly in New York. And they produce ACE plus Samudra, and they call it Samudrace. And I think it's the first state-of-the-art coupled ocean atmosphere climate model emulator. So that's one solution. That's not what I work on. So I'm going to talk a little bit what I work on, which is a different strategy. I'm in Switzerland, so I can play the Switzerland card, like not committing to what will work best and studying different solutions. I think it's nice that there's an ecosystem of solutions, but I'm presenting 2 that I think have a shot in the out-of-distribution setting. So there's many solutions that don't have a shot because of what I said earlier. The hybridization paradigm is you're going to keep what we call the dynamical core. So that's Navier-Stokes, coupled Navier-Stokes integrated forward in time. And then in Earth system modeling, you have this modularity assumption where you couple these Navier-Stokes with a bunch of different processes. Like how do plants, how does photosynthesis work? How do storms respond? How does chemistry work? These are not in Navier-Stokes. So there's a bunch of different models of processes we can't directly model with PDs that are called parametrizations. And many of them are empirical or uncertain. So the hybridization strategies is you target those that are most uncertain and you replace them with machine learning. So you start from all physics-based, but be careful when people tell you it's physics-based. Sometimes it's just like someone drew a line between 2 asymptotes. So when people tell you physics or chemistry-based parametrizations, you should always be skeptical. And so that's why it's so easy to replace some of them with machine learning, because some of them are not that good. They're just but it's not that people made poor parametrization, it's just that they worked with the data they had at the time. And I see that I still have 16 minutes, so I'm going to go fast, so I'm going to skip some examples. And how much time do we want for questions?
Up to you. We have the break in 17 minutes, so if you manage to finish in 12, it would be perfect.
Okay, so I'm going to skip over some examples, but I'll share the slides, and you can always go back to the papers, etc. I'll talk about what I work on. I work a lot on how to better represent storms and clouds in climate models. And of course, we can learn from observations. It's often hard. Observations are noisy, they're sparse. So one really promising direction is that it's been now 15-ish years that different modeling centers around the world have been able to run what we call storm resolving simulations. So these are simulations at the global scale that have a nominal grid spacing smaller than 5 kilometers. So they can resolve storms of 10-ish kilometers. And what you can do is, they're way too expensive to run routinely for climate projections, but what you can do is you can use them to learn the relationship between the environment, the coarse environment, and how storms respond. And so I was going to show you 3 examples, but that's way too ambitious. So I'm probably going to show you one example. And the one example that's easier that I like to start with is cloud cover. This is a video of the North American monsoon to show you that actually it's not that easy. So imagine you have a big voxel and you know the average properties of that voxel. You want to know the volume of the area in that voxel that's occupied by clouds. So what you do is you're going to take, I'm going to skip the technical details. You're going to take these really high resolution simulation and you're going to coarse grain it to see the cloud fraction from the perspective of a coarser climate model, a cheaper one that you actually have a shot at running to make climate projections. So you take that high resolution data, you say if there's more liquid on ice than a certain value, it's a cloud, so you have a bunch of zeros and ones, then you count these zeros and ones and you get cloud cover in percent. Now that you have cloud cover, you can take the average environmental properties in your column, and then what you can say is, all I have to do now is to learn a mapping from the left to the right. You're back in a supervised learning problem. You can just say, I'm going from X to Y. I'm going to minimize Y minus what I predict. So now I'm going to show you, and this is based on another paper where I argue on how you can distill complex machine learning models into simpler one. So I'm tracking the validation mean squared error performance on the y-axis. You want to go lower, and then complexity, but this is a naive measure of complexity, is number of trainable parameters is on the x-axis. You want to go to the left if you want your model to be simple. So you're trying to go to the lower left. You start with a bunch of baseline. The model we're trying to beat is at the top. It's easy to crush because it was developed in the 80s, back when you have like only 1 or 2 reliable variables in your climate model. We train neural networks. We crush all the baselines because that's what machine learning is really good at. You find very quickly a very complex model that performs well. And then here the difference is that we wanted to do equation discovery because we thought cloud cover may have a simpler representation. So we use a neural network, we identify the variables that are most informative in the nonlinear sense. So we do sequential feature selection with simple neural networks. We say, okay, these are the fields we really need to predict cloud cover. Now that we only have a couple of fields, and we made a local approximation, so we test which inductive biases are most appropriate using neural networks. We can throw this in a symbolic regression library. It doesn't really matter which one you pick. Here I'm picking PySR because it's really good, it's user-friendly, it's evolutionary algorithm-based, so it sometimes combines functions in a way you didn't expect, so you can discover things. Actually, the developer of PySR is a Cambridge professor, Niles Cranmer. He's like incredible, like what he puts out. It's helping so many fields. And so in that case, I'm not going to go too long. We have papers on this. It's really nice. We find a 3-term equation with terms we didn't expect. This is a Taylor expansion, but these 2 terms are new, and they have physical meanings. So it took us years, but we did discover a new equation, a new parameterization that was better than what was before. We went all the way back to physical understanding. We can derive them from at least first-ish principles. And now we plug it back in the climate model, and we say, okay, we have this new parameterization. We did this whole development cycle with machine learning, which is, by the way, I think one of the things AI is best at. It allows you to really quickly iterate through your model development cycle in a way that traditional models don't allow you to do. So it's not immediately giving you a discovery, but it's giving you a hypothesis cycle, where you can very quickly formulate hypothesis, improve your model, go back. So I think that's where there's a lot of potential. We take that newly discovered equation, we put it back in the climate models, and then now we use observations, satellite, etc. And we see, okay, can we better describe the historical climate? And we get a better cloud cover. And I say we because this is collaborative. This is led by a colleague at the German Aerospace Center. I closely collaborated with the student who discovered the equation. It was a lot of fun, many years. But again, much faster than traditional methods. We get better clouds, better radiation, which is important for climate change. And that's super promising. But this is for what I would say an easy case because we replaced what we call a diagnostic parameterization. So this is a variable that doesn't feed back on Navier-Stokes. So in a way, it's not too dangerous, right? You can predict whatever you want, you're not going to crash your model. And the other slides that I had were about harder parameterization, what we call prognostic parameterizations, where you also learn to feed back on the coupled Navier-Stokes. And that's much harder because you can crash your models. I think for the interest of time, I'm going to give you a brief overview, and then during the question session, feel free to ask anything you want. I want to advertise this benchmark dataset called ClimSim. So that's a huge team, and we put together, I would say, what was the first benchmark dataset for machine learning parameterization, where we clearly spelled out what was X, what was Y, what was a good target. It was published in NeurIPS, and then it was so well done that the team, I mean, really, Jerry Lin gets a lot of the credit here, managed to convince Kaggle to run a $50,000 competition based on the benchmark dataset. And so what we did, and I think it's the first time we did that collectively, I mean, it's nice to be a very collaborative community, is we crowdsourced solutions to the problem. And with $50,000, you can get a lot of teams involved. And we got some crazy architectures we would have never thought of. So, you know, initially the UNet was the best we had, and these are the architectures from the top 5 teams. And what matters was not just the architecture, right? The architecture you mostly needed to be expressive enough and have inductive biases and not crazy. What's funny is the one that used what we call a squeeze former, so it's like a voice processing algorithm. And that one to predict turbulence and storms in the atmosphere. But also all the strategies that go next to it. And then for a year, as a team, we worked to put it back in the climate model and see how well it was doing. And what was really interesting is we couldn't really anticipate exactly. So for example, some of the strategies that were developed. So for example, okay, I'll spoil a couple of strategies because I think that can work for completely other fields. My favorite one, I think, is also used in AlphaFold, is what's called a confidence loss. You ask your neural network to predict its own loss. It sounds crazy, but it works super well. Because it just makes it converge faster, and then it gives you an uncertainty estimation for free, and it's usually quite well calibrated. Another strategy that worked, which is very counterintuitive to me because I'm a physicist and I like simple things, is if you don't know how to normalize your features, you can just concatenate different normalized versions of your features. So you say, okay, normalization 1 concatenated with normalization 2 concatenated with normalization 3, which to me sounds like complete overkill, but I guess with enough data and an expressive enough architecture, it works. And so what's interesting is such strategies give different results depending on the architecture. So it's not a trivial thing where strategies will work the same way across UNet, squeeze-former, conv, next, and all the different architectures. Like some work way better on certain architectures than others. But then problem, even if it works quite well, everything is stable, we stuck with systematic biases, which means it's not enough to just work with a single climate model and setup, and actually that Earth system model, as good as it is as a sandbox, I don't think is going to be continued. And so some of our work tries to just isolate the storm part, the convection, and other climate model. I'm not going to go through it all, because these are fresher results, but we were inspired. We made a mixture of experts based on that confidence loss, and it works super well. So you can also work that, if your neural network knows how good it is, you can also use that to say, okay, if I'm not very confident, use the physical parameterizations. If I'm very confident, use the machine learning one, and that works super well. So that's another use of the confidence loss. I'm going to skip it. I work with Klima, that's a Caltech group. They really care about Bayesian statistics. So if you're in an inverse modeling setup, you can either do what I showed you, where you first train a neural network, you put it back, you hope it works, you have a bunch of tricks to make it work, like adding noise during training. If you know aggression, like you can use these tricks and it works. Or you can frame the whole thing in an inverse modeling problem, and you're saying, okay, I'm gonna couple it, run it a bunch of time, and then based on the time mean statistics, use, for example, ensemble, Kalman inversion, or any update rules you have on the trainable parameters based on the statistics, the error statistics, to update the parameter. And you can set that up in a very, very clean way. So there are inverse modeling frameworks that also allow you to train such neural networks inside bigger models. And I think that gives you a good overview of what you can do for climate. My last argument is, and I'm going to do a really, really, really poor job at it, so my message is it'd be great, and maybe you all do that in your respective fields, but I think it's really important when we say AI is going to accelerate everything, that we actually measure how much it accelerates everything. So here is not even apple to orange, I don't know how to call it, like an apple to grapefruit comparisons based on a bunch of data that I could get from different models. What I looked is, I looked at the throughput of each of these models. In climate science, we quantify it using simulated year per wall clock day. That's divided by the number of GPUs I run it on and the number, I'm saying I only ran maybe one of these models, the rest is just from papers, and the number of prognostic variables. And if you look at the function of horizontal grid spacing, it looks like the climate models are the AI-based climate models are super effective. But then if you do a different kind of rule, so you really look, you really take into account the time steps and the number of vertical levels, etc. If you compare AI-based climate models to GPU-ported models, so you have to be careful to compare it to GPU-ported traditional models to make sure you're doing, it's still not an apple-to-apple, but it's closer to an apple-to-apple comparison. They all fall roughly on the same line. And what that suggests, and I think we only started to systematically study it, is that AI models are not intrinsically faster. They do run on GPU, so that's a big advantage. What they're good at is that you can directly target a given spatiotemporal resolution, and you're not constrained by typical numerical stability considerations, where you would need to reduce to a tiny, tiny, tiny delta t because of the CFL condition. You can directly target the spatiotemporal resolution you want. And I think the scaling is not that different, but the difference is you can directly get the resolution you want. And that's a huge advantage because, and so here I'm proposing like more systematic way of studying it. You could define an effective resolution based on power spectral densities, or you could base it on entropy if you calculate the likelihood. But I think traditional models have a nominal resolution, right? You run them at 2 kilometers, but really they have an effective resolution because there's all these numerical diffusion, etc. So all the traditional model, at least in fluid dynamics-like problem, will have an effective resolution that's up to 5 times poorer than what you think you're running. And so I think when we think about AI to replace, accelerate some of these models, that's really one of the best advantages is that nominal resolution is going to be much closer to effective resolution. But to show that systematically, you need to run all of these models on the same hardware, which is not trivial. I can get estimates based on things reported in papers, but what you can do at the individual level is you can always report your hardware, how much time it took you to train, how much time it took you to make a given inference. And if you do that every time you publish a paper, which is not that hard, usually you have that number, you just lose it if you wait for long enough after the paper publication. So just if you write that in every one of your preprint, I think we could really make progress in better understanding the scaling of our models, and also for sustainability considerations, because I mean, eventually people are going to say, okay, use all these resources for what? And having the scaling will really help you justify whether your model is sustainable or not. And this is my conclusion, okay, taking a step back. One of the biggest challenges in applied machine learning, and I think that's true across scientific field, is the out-of-distribution problem. These models are incredibly good at interpolating given enough data and given an expressive enough architecture, but where it's struggling in every single field is out-of-distribution cases. So the whole trick is how do you handle them? And I don't think there's a universal answer. I think every single field is going to have different strategies. What you shouldn't do is just pretend it's okay and they do well, because some early papers did that and it's not true, right? You can switch the activation function of two neural networks that seem to do just as well and get completely different asymptotes and like completely different behaviors. So it's not true. If you go out of your training set, really outside of it, there's zero guarantee. So you should look at what it does and you should come up with ideas. And there's so many ideas you can all come up with. And it's a really fun game to play too, on how to handle out-of-distribution cases. For weather, I think the out-of-distribution cases were extremes, but I think we're actually going to solve that I think we're going to make a ton of progress on that in the coming years as a community. For climate, it's not so clear. I think we know what the challenge is, but if I had to guess, it's going to take a lot longer and different strategies. Another thing to consider for multi-scale AI modeling is the fact that you can use super resolution algorithm to switch from one scale to another. So that's something you can play with if you're thinking of scaling. You can always integrate in time at a given scale and then super resolve as needed. But finding the exact right balance is going to be field dependent, and I don't have time to talk about it today. That's a whole other talk. And with that, thank you, and I think we have no time for questions.
In the interest of time, we should focus mostly on online questions, if there are some. Because on-site participants can ask at the break. Are there any online questions? An urgent on-site question, maybe? Yes.
Okay, so thank you for the great talk. I would like to come back to the climate model and the interaction between the Navier-Stokes equations you are talking about and the other
components, parameterizations,
yeah. Because at some point you say, oh, in this case there is no problem because it does not interfere.
Feedback,
feedback.
Yeah.
And so, how do you know that? Can you be a bit more specific? I mean, is that assumption, obvious assumption, or is it something?
Yeah, these are built-in assumption of you. I mean, it's also things we know, but it's mostly built-in assumption of a model. So, for example, cloud cover, the fraction of clouds in your box. We only use it to calculate a bit of how the radiation works and how what we call the microphysics works. So this is getting into details of climate modeling, but so we know that to first order, it's not going to change the temperature and the moisture field. In contrast, convection, which are all the movements driven by density differences, that's going to change. That's going to result in fast vertical transport. And so that's an order 1 change on your main prognostic variables. And so any process that's an order 1 change on the dynamics is much harder to model, because then you have to make sure the coupled dynamical core and model behaves well. And so you can, basically it's an inverse problem.
In that case, what do we call BL square limit? So this is your inherent loss function.
I mean, there's some trivial consideration, which is the model doesn't crash or blow up, which sounds easy, but takes a lot of time. There's some obvious bugs that you correct, right? But then you could imagine an emulator that does really, really well, but that when coupled leads to unstable mode, for example, because of eigenvalues that are misbehaved in your dynamical operator. And that's not something that's necessarily trivial to solve. We've learned tricks over the years. So for example, one trick that works really well is if you know your system is smooth-ish, you can train with noise in the feature space to just ensure that you don't have big discontinuities in the response when you change the inputs by a tiny fraction. There are fancier mathematical ways of doing it, of course. You could also, constrain your Jacobian Hessian with automatic differentiation. So you could imagine all kind of tricks. But these are the kind of problems you're going to run into, so stability. And then there's the cost function problem, which is that you don't just care that the tendency at t plus delta t is good. You care that the coupled trajectory, after you integrate for many time steps, stays on the right attractor, for example. And that's much harder to train and to constrain. Yeah. Yeah.
Okay, thank you very much again.